Hello students, today we will learn mole concept. First of all, what is mole? Mole is basically a counting unit. Of amount of substance. Now, counting. Counting means we have numbers to count. Like 1 dozen is equal to 12 units. Where 1 dozen is a counting unit to count 12 particles. Similarly, a mole is a counting unit to count amount of a substance, and its value is now. How can we get this value? We will describe it later, but the thing to know is that mole is a counting unit which is used to count this much amount of particles. So look at this term. This is a very big term, so it means mole term is applied to microscopic particles. Now, which microscopic particles? Microscopic particles like atoms, molecules, electrons, protons, etc. etc. Now, scientists are discovering elements from the 13th century, and they have seen that the elements are found in compound state, and for this they make some laws that how these atoms or elements combine with each other to form compounds. This lead to make some laws in chemistry known as laws of chemical combination. The uh, the first law in this, first of all, see this term, combination of chemicals, means we are combining or reacting the chemicals, means atoms of elements, molecules, etc. Now the first law is law of conservation of mass. As the term suggests, we have to conserve the mass, means it can never be created nor be destroyed. So this law is also known as law of indestructibility. According to this law, suppose reactant A is reacted with reactant B to give product C and product D. This we have reactant 1, reactant 2 to give product 1 and product 2. Now we are talking about conservation of mass. So mass A of reactant A, mass B of reactant B reacted to give C mass of product 1 and D mass of product D. So according to this law, A plus B is equal to C plus D, where A, B, C and D are all masses. This concept was introduced by Jean Ray, but the whole credit goes to Antoine Lavoisier. Because he stated and described this law. Now take an example, simple example, H2 plus O2. We know that it gives water. Balance this chemical equation. So balancing is done. Hydrogen, oxygen, water. Now as we know that mass of hydrogen is, which we are taking to react, is 4 gram, and oxygen is 32 gram. So the product will be formed of 36 gram. Now look at the left hand side. 4 plus 32 is equal to 36, which is equal to product side. It means laws of conservation of mass suits it. But as we know from the first law of thermodynamics of physics, that every machine doesn't have 100% efficiency. So we have two cases for this law. First is case 1. If all the reactants get converted to products, so mass of reactants will be mass of products. But in the case 2, suppose the whole reactants will not converted into products. It means initial mass of reactants is equal to the final product form plus mass of unreacted reactant. But what happens in the nuclear reactions? We said that some mass is lost because of phase formation, so the mass get converted in the form of energy by the Einstein's simple formula, E is equal to mc square. So law can be modified as law of conservation of mass and energy for nuclear reactions. This law was later on verified by scientist Landau. Now the second law is law of constant proportion. Second law is law of constant proportion. According to this law, the mass ratio of constituent elements in a compound is always constant, irrespective of its source or method of formation. Now take a look at the definition. Mass ratio of elements is always constant. That is, take an example, water. Here the mass of hydrogen is, and the mass of oxygen is, particularly in hydrogen. So for water, the ratio of mass of constituent elements, that is hydrogen and oxygen, is 2 is to 16, that is 1 is to 8. Now if we take water from sea or tap or river, the ratio will always remain constant. This means this law suits for all the compounds. Now talking about the exceptions of this law. This law doesn't apply on isotopes. That is, take the same example, water. If we are taking isotope of hydrogen, that is whose mass is 2, then the ratio becomes, that is 1 is to 4, which is not equal to our previous ratio. It means this law is not applied to isotopes. The second exception is for non-stoichiometric compounds. Non-stoichiometric. These are basically those compounds whose atoms are not present in the whole number. That is, FeO, wustite is the name of that compound. The iron is present in 1 minus X ratio according to oxygen, whose range is from 0.83 to 0.95. As these values vary, so it means law of definite proportion doesn't apply to non-stoichiometric compounds. And the last exception of this law is reverse statement of this law is not true. Now writing the reverse statement. If the mass ratio is fixed, then a particular compound is obtained always. But this statement is wrong. Taking example, suppose we have a hydrocarbon in which carbon mass is 24, hydrogen is 6 and oxygen is 16. It means we have 2 atoms of carbon, 6 atoms of hydrogen and 1 atom of oxygen. Writing the formula C2H5O OH, but we can have another form also, that is CH3O CH3, where both contains C2H6O, this much number of atoms of the constituent elements. But this is, we know, this is alcohol and this is, so going back to the statement, here the mass ratio is fixed, that is fixed mass ratio, but a particular compound is obtained always. This is not true. It means the reverse of this statement is not true. This is one of the exception of this law.